Okay. So we saw till, or we discussed till the four fundamental subspaces last time, right? So we will look at linear independence. We'll come back to linear independence now. Let's say we have a set of vectors V1 to Vm belonging to Rn, and we want to know whether this set is linearly independent. Okay, and we know how to find that out. You simply take the linear combination of these vectors with some scalars a1, a2 to am, equate it to the zero vector. This should be bold zero. Equate it to the zero vector, and you solve for a1 to am. Okay, and if the only way you can get this equation to be satisfied is all the ai's are zero, then you say it's a linearly independent set. That is equivalent to saying, well, I will form a matrix like this, but the columns are all the vectors that I'm interested in, or the set of vectors that I'm trying to investigate. And the scalars that I have, a1 to am, I can put them as a column vector, and this matrix multiplied by this column vector is essentially this, because a matrix post multiplied by a column vector is essentially you're taking the linear combination of the columns. So if you want to find out if a set of vectors is linearly independent, then you simply take the set of vectors, form a matrix, and then solve this equation. X is unknown in a set of scalars. Okay? Essentially, you're saying, well, if you call this matrix V, you're saying find the null space of this matrix V, because null space of a matrix is essentially all the values of X that will map to zero, right? And if the only possible solution is, or if the null space is only the zero vector, then you know that the set of vectors formed by the columns of the matrix are linearly independent. The moment you have any other value here for the null space of V, then it's a linearly dependent set. Or equivalently, if the rank of, so for example, if you have m vectors, if the rank of the matrix is m, then the columns of the matrix V are linearly independent. Okay? So essentially, you can find out linear independence by simply solving a set of linear equations. And whenever you see a statement that says the rank of a matrix equals the number of columns, that is equivalent to saying the columns of A form a linearly independent set of vectors. The same thing applies to the rows as well. If the rank of a matrix is equal to the row rank, then the rows are all linearly independent. If it's equal to both, then both the rows and the columns form linearly independent sets. And that's essentially what these two are for. Okay. So now, if we had well, one of the problems in the quiz, the last problem, right? Based on the discussion now, or what was the answer? Did anybody attempt it? The last one, where you were asked to find out if the columns form a linearly independent set? No. Okay. Based on a discussion now, can you say if they form a linearly independent set or not? In the quiz, yeah. Yeah. Last question. Yes. A, there are 5 columns, and the question is find the homogeneous solution. But my question is different. Do the columns of that matrix form a linearly independent set? Based on just this slide, you should be able to answer it. Okay. Why do you say that? No, that is always, see, 0 will always give you 0, but that's not enough. If the only thing that gives you 0 is the set of scalars being 0, then it's linearly independent. If there is anything else in addition to 0, then it's linearly dependent. Are you sure? if I add the first two columns, I get the third column. No, sorry. No, I don't. But for sure, there is a way you can represent, let's say, 1, 3 in terms of 1, 1 and 1, 2. So it'll turn out that this is a linearly dependent set. But if you look at this statement, right? What is the maximum? What is the maximum possible rank for that matrix in that problem? No, what is the maximum possible rank for any matrix? No, it's the minimum of the number of columns and number of rows. No, here it's 2, right? The maximum possible is 2. But how many columns do we have? 5. That means the rank can never be 5. That means the rank can never be m. That means it has to be a linearly dependent set. Because for if it's actually, this goes both ways. If the rank is m, then the columns form a linearly independent set. If the columns form a linearly independent set, the rank must be m. Okay. Here, the maximum possible rank is 2. That means the rank can never be the number of columns. That means this has to be a linearly dependent set. Okay. And in fact, if you solve for the set of homogeneous solutions, you'll find that it's more than just the 0 vector. Now, if I ask you if the rows are linearly independent, what would you say? Yes, maybe, always. Yes, okay. Why is that? Okay, correct. So here the problem is a little trivial. The second row is not a scaled version of the first one, so they form a linearly independent set. And my argument still applies. The number of, what is the rank then in this case? The rows are all linearly independent. That means the row has to be the number of rows. Sorry, the rank has to be the number of rows. Right? It's 2. And that's essentially the question, the point here. If the rank is equal to the number of rows, then the rows form a linearly independent set. Or if the rows form a linearly independent set, then the rank of the matrix is the number of rows. Okay. Now we come to the last topic in this module, which is essentially, well, we said there are 4 fundamental subspaces associated with each matrix. And with subspaces, we can associate the idea of a dimension. What is the dimension of a subspace? Yes, the number of vectors in the basis set for that subspace. Right? Okay, good. So I'll simply state what the ranks are. We won't go into details of why it is like this, okay? But it should feel intuitive. Now we have 4 fundamental subspaces. What is the column space, if you remember? Yep. Yes, it's a span of the columns of the matrix A. Okay. Let's say we have a matrix. As always, we have a matrix A, which is n cross m. Okay. And let's say the rank of it's a rank deficient matrix, or the rank of the matrix is R. And for sure, R is less than or equal to minimum of n cross m. Okay. If we have a matrix like this, then the dimension of the column space, okay, is essentially equal to the rank of the matrix. Okay. And similarly for the row space, what is the row space? Span of the rows of A. The dimension of the row space is then R as well. What about the null space? What is the definition of the null space? Yep. Set of all vectors? 0. Okay, all right. whenever you have a matrix, there are two spaces, right? Input space, output space. Rm is the input space, Rn is the output space. What space does the column space belong to? Output space or the input space? Okay, it's the output space. Okay. So this is a subset of, or this is a subspace of Rn. The row space is subspace of Rm. What about the null space? Does it belong to the input space or the output space? Yes, it's good. This is R. It's possible I've mixed up N and M here. So I'm going to go back. I should have written it down. So we saw last class that the input space is divided into the row space and the null space, right? What is the dimension of the input space? It's n. The overall dimension of the input space is n. The dimension of the row space is r. So it turns out that the dimension of the null space is essentially n minus r. Essentially, whatever dimensions are left, that's taken up by the null space. Similarly, for the left null space, the same argument applies. The output space has a dimension m, that is because it's Rm. The rank of the matrix is R, and the dimension of the column space is R. Whatever is left is then taken up by the left null space, which is essentially m minus R. Okay. From this now you can tell me, let's say I have a matrix, m cross n again. Okay. What if R is equal to n? What can you say about, well, the dimensions of the four subspaces? Null space is 0. Let's assume m is not equal to n. Null space is 0. What about the row space? N. Row space will be n, that's all. Okay, what about the column space? No, here. Simply have to just repeat this. R is equal to n. The column space will have a dimension n, and the left null space will be m minus n. That's it. Okay. If m is equal to n, then the column's left null space will also have dimension 0. Okay. Now, when the rank is equal to n, no, the number of columns, the dimension of the null space is 0. That means the null space has to be this, just the 0 vector, which is essentially what we saw earlier, which is equivalent to saying if the null space has dimension 0, then the columns form a linearly independent set. Okay. What about when R is equal to m, the number of rows? Yes, the dimension of the null space. What is it? Dimension? Yeah, dimension of the column space is m. Dimension of the row space is m. Dimension of the left null space 0. Dimension of the null space would be n minus m. That's all. Yeah. Okay. All right. So that's essentially everything that I wanted to cover for the module on solutions to linear equations. And for the midterm next week, which is on the 4th. So this essentially covers everything for the assignments, okay, which is due on the 30th, right? and then we will have the midterm on the 4th. I think orthogonality is included in the midterm. I will just verify that. Okay. But we will cover, actually maybe no, we will just stop here so that you have time to prepare. Your midterm on the 4th will essentially have everything till whatever we've covered today. Okay. Are there any questions so far in all the modules that we've covered? The 3 modules we've covered? No? Okay. Okay. Have you started looking at the assignments yet? Okay. So in assignment 1, there are a couple of programming assignments. Okay. Did you try to run the Jupyter notebook that is there? Case study 1 and 1B? No. No, is it? Then what did you... Anyway, doesn't matter. Okay. So if you go to the course page, if you click on assignments, no? Let me see if I can open it. Yes. Were you able to open this and run it? Execute it in VS Code? Okay. You should try and execute it. If it does not work, you should contact us. Yeah. Okay. Okay. So these 2 are included in your assignment. So there are questions here that you need to go through and answer. Okay. I'll just introduce the topics or the ideas that are there in those notebooks, which is essentially an application of, again, ideas from vector spaces and matrices. Okay, and in fact, one nice application of matrices. Okay, the 2 case studies, they essentially deal with analyzing clinical notes written by doctors or clinicians. Okay, so in case study 1, we are looking at if you have a bunch of notes written by doctors, but we don't know what specialty they are from, is it possible for us to do clustering to see if clinical notes from neurology all cluster together, cardiology cluster together, and things like that? That's essentially what we are trying to do in case study 1. So the description of the problem and all that is already there in the notes, right? The initial set of instructions will tell you how to set things up. I won't go through the code. You can go through the code yourself, and then if something's not clear, just come and talk to us. Okay. You will need to download the clinical notes. That's essentially a data set from Kaggle called reports.csv. You'll have to download it and copy and paste it into this folder in data case study 01 folder. Okay. You can copy paste that reports.csv, and then you should be able to then run this notebook. And the data set that we have is a .csv file. It's comma separated value. Do you know how many of you don't know what a comma separated value file is? All of you know what it is. Okay, all right. Then I won't go into the details. There are 2 columns that are of interest to us. I think there are only 2 columns to this. There is a column on medical specialty. There is a column called medical specialty, another column called report, and both of these contain textual data. Right? That means they are strings in Python. Right? So what we want to do is to then see, let's assume we don't have the medical specialization column. We'll assume that we don't know what specialization each report is from. And we want to simply take these notes and then do a clustering algorithm to see if notes from a similar specialty all cluster together. And for example, notes from PMR are very different from notes from, let's say, hematology. Okay, something like that. That's what we want to do. But the clustering algorithm that we've discussed in this class so far, what is the clustering algorithm called? K-means, right? But the K-means algorithm was something that worked on numbers, not text, right? So if you had n vectors, we can simply run the K-means algorithm by simply choosing the K that you want, and then see if you get clusters that look meaningful. Okay. But the problem is the reports are text data. Question is now how do we now get numerical data from this text data? Right? There are several ways to do this. We look at a very simple way or a rudimentary way. You can convert a text data into a set of numbers that tell you something about the text. Okay, and this method is called count vectorization. It's very simple. Okay, you have a text. Okay, in addition to the text, you have what are called tokens. Okay, these are tokens are essentially a list of words that have some meaning for you in your area of application. Okay. Count vectorization, all you're doing is I take the text, I have a set of tokens, I count, let's say I have n tokens, right? I count how many times each token appears in my text, and I simply put a number corresponding to that count, right? This is an example of that, right? Let's say we have this text, okay? And the tokens we are using are quick, brown, fox, lazy, and dog. When you say you're doing count vectorization, you're simply counting how many times does quick occur in this text, how many times does brown occur in this text, so on and so forth. So if we simply count, right, if there are n here, if you do the count vectorization process, you should then get an n vector, right, where the ith element in that n vector will tell you how many times token I appeared in my original text. That's all, right? And now, once you have the count vectorization, we'll simply assume that this count vector simply contains all the relevant information that you need for this clustering process. It might not, but as a first step, let's say this is good enough. If this is good enough, we can stop, and it will turn out it's not good enough, which makes sense. Language is simply not how many times do different words occur. There is it's not just what words and how many times they occur. It depends on what is the word before, what is the word after, and the context and all that, right? But this is how you start anyway. A simple approach to see if it works, right? And we'll essentially just do this. So we'll take the medical reports. Let's say somebody has given us these tokens. Okay, we give you the tokens. Okay. Then what we will do is we will take these tokens, compute the count vectors for each of those reports. So each of them will be an n vector. So now you have, let's say, m n vectors. M is the number of reports, n is the number of tokens, right? You want to cluster these m n vectors into, let's say, k clusters. That's essentially what we're going to do. Okay. As you run the code, you will understand what each one of them does. And if you've not done a lot of Python programming before, this is also a way to learn how to do different things. Okay. So we read the data first, and the data looks like this. I said there are two columns: medical specialty and report. So the first row of this data is from cardiology or pulmonary medicine, and there is the corresponding clinical note or report. It looks like the first few are all from cardiology. And if you look at the data set, right, it's got thousands of notes, essentially from 5 different specialties: gastroenterology, surgery, radiology, neurology, and cardiology. And these are the number of reports that we have. So we essentially have about 2,000 notes, slightly more than 2,000 notes. Right? We do some pre-processing. For example, if you look at these notes, right, they have both uppercase and lowercase letters. As far as the computer is concerned, uppercase letters and lowercase letters are different. And if you look at the tokens that we give you, they're all in lowercase. For example, if I have cardiology with capital C in my text, but I have cardiology with small c in my token, if you do the comparison, Python will tell you they don't match. Okay? So we need to now first convert all reports to lowercase. That's essentially what we're doing here. And we've created a new column called report lower. That means report with the text in all lowercase letters. Once we do this, we then read the tokens file. This should actually be 50. We'll change that. There are 50 tokens. So that means each report is converted into a 50 vector. So if you run it, you'll see that the number of tokens is 50. And the tokens are this: impress, palpitation, gallop, compare, non-significant emphysema and all that. So we're essentially going to be counting how many times these different terms occur in each of our report. Once you do that, we then have a small function here, which will essentially take the clinical note, take the list of tokens, and then simply return the n vector, that is the count for each of the tokens that you have. And again, see, you should understand what is written here. Okay, if you're not familiar with Python programming, then you should take a look at this and then understand, so that later on you're able to write these things on your own for the problem that you might be dealing with. Okay. So once you do that, this is essentially what we get. So I'm simply printing here, I don't know, maybe 10 different rows of the data and their corresponding count vectors. Okay. This is row 732. That means in our original data, I take the note corresponding to the 732nd row, 732nd row, and then I'm printing the count vector here. So it looks like in this, all the initial terms do not appear, and then this term, I don't know what index that is. That's 1, and then there is another one. So at least in row 732, only 2 of the tokens that we are looking at appear, and they appear only once. Okay? Now, if you look at another row, let's say this one, 2116. So 1216. The third token appears once. The 6th token appears once, and then a few other tokens appear as well. This token appears twice, and so on and so forth. And there are other cases where a particular token actually appears multiple times, 10 times here. This one appears 5 times, and so on and so forth. So now what we essentially want to do is we get rid of the text, and we simply use these n vectors to now do the clustering for us. And remember, this is in a 50-dimensional space. Once we've done this conversion, then the clustering is essentially the same as what the dimension of the vector itself does not matter. We know the procedure for doing the clustering algorithm. You can either use the k-means from a built-in Python library. We've implemented k-means as part of the library that we've sent you, that we share here. And in this notebook, at least, we've used our own clustering algorithm, implementation of the k-means algorithm. And when you run the algorithm, right, we can look at the clustering cost, jclust, which initially starts at some value as high as 13,000, quickly drops, and then it essentially converges to, after about 9 iterations of you updating the cluster center and the cluster assignment. Right? And after this, it remains the same. So in essentially 10 iterations, it's identified the number of clusters we want. And because we knew from the start that there were nodes from 5 different disciplines, we chose K to be 5, essentially to see if this process of representing our nodes using the simple count vectorization method actually captures all the information relevant to separating each of the 5 disciplines out. That's why we chose it to be 5, so that we can then go back and compare if cluster 0 contains, let's say, mostly nodes from cardiology, if cluster 1 contains mostly nodes from some other discipline, and so on and so forth. If we find that, then we say, oh, actually this clustering algorithm actually works quite well. Then maybe in the future, if you get a new node, right, where you don't know what the specialization is, you simply compare which cluster does it belong to based on the cluster centers that you already have, that you've identified using this data set. And when you do this, what we find is essentially this. Remember, in a real application, you might not know the labels for your clusters. You might not know what the clusters mean. You only know that they are all similar. Okay? I'm sorry, I think I've used 4 clusters, not 5. Yeah. So we've set K to 4, and we've run the clustering algorithm using our approach for converting the text into some numerical representation. When we do that, we do find 4 clusters because we've asked it to find 4 clusters. Looks like cluster 0 or the first cluster essentially contains nodes, well, contains the maximum number of entries. So if you add all of these, that's the number of entries that have been categorized as cluster 0. If you add all of these, that's the number of reports that have been categorized as cluster 1, 2 and 3. If you look at this, right, it looks like this cluster 0 contains data from all nodes. So essentially that means, well, our method is not that great. It's not, at least the simple way of having a bunch of tokens and then counting how many times they appear and using that to cluster does not do a great job. Right? Second cluster, on the other hand, also seems to have an equal representation for all the 4 specialities, but the numbers are somehow smaller. So it turns out maybe these nodes are somehow slightly different from the ones corresponding to cluster 0, at least based on the way we are capturing information about the node, essentially the count vectorization method. And that depends both on, that primarily depends on the tokens we've used. Maybe if we had used a more richer set of tokens, maybe that would have that will definitely lead to a different set of results. And maybe it would have led to better results that we are looking for. Cluster 2 and 3, on the other hand, seem to be a little bit more specific, even though they only identify a very few number of they only have a few number of items. For example, cluster 2 appears to contain mostly nodes from gastroenterology, and cluster 3 mostly contains, or in fact only contains, nodes from cardiology. So even though not a great method, it looks like this approach does have some specificity towards these 2 disciplines, at least in the nodes that we have. Okay. And in fact, one thing we can do, we have 4 clusters. We could ask, well, what are the cluster means for these 4 clusters, and you can plot them like this. These are cluster means for cluster 0. So there'll be 50 of these numbers, and these are the token text corresponding to each of the 50 tokens that we've used. So the first token is impress, second is palpitation, gallop, so on and so forth. Okay. So what we find here, see, here it appears like most of the values for the cluster center is 0. That means the tokens we've chosen actually don't appear a lot in the text that we have made. So the token is not that great. Tokens we've used are not that great. In fact, we saw that already here. Most of the numbers are 0. This should have already told us that we are essentially working with tokens that are not that well represented in the text that we have. And the reason you have almost all, I mean, majority of the reports being sent to cluster 0 is because these are essentially nodes that essentially have very poor representation in terms of these tokens. Okay. But if you look at 2 and 3, right, there is a spike for a couple of tokens. For example, there is a spike for, I don't know, ladder. Okay. And for some reason that leads to us identifying 21 of the gastroenterology nodes very specifically. And cluster 3 has ensure and ending. And that for some reason has led to us identifying mostly cardiology-based reports. So the point I'm trying to make is when you're talking about clustering text and stuff, how you convert it into a number matters, and in fact that applies for any approach that you take. When you're doing data analysis, you might have a bunch of raw data. You might then compute a few numbers from that, thinking these actually represent something about the application that you're dealing with, and then you use those numbers, which are called features, to then do some classification, regression, or clustering. Right? The count vectors are essentially features. Right? It's the same idea. It just turned out that in this particular case, the features that we've chosen were really not that great in terms of clustering these nodes. Okay. So as you go through this document, right, I don't think there are questions early on. Yeah, there are a couple of questions at the end of the document. Okay. So based on what has been provided to you, you are required to then answer these questions as part of your assignment. You can go through them. If it's not clear, you can come and talk to us. Okay. So that's essentially an application of clustering that we discussed a couple of classes back. Okay. The other case study that we will look at is actually an application of matrices. Okay. This has to do with not clustering of nodes, but we want to know we have a bunch of terms, right? Let's say the same token file, right? Let's assume we have no understanding of what those terms mean. Okay. And we would at least like to know in the tokens that we have, which of the tokens are concepts that are related to each other. Okay? When I say these are concepts that are related to each other, that means they are likely to occur in the same context. For example, if I have two terms from a particular specialty, if they represent a similar thing, at least medically in this application, then they are likely to occur in the same node regularly. If these are completely different ideas, right, that are not medically related, then if one term appears, the probability that the other term will appear is not that high. That means they don't occur together. So this idea of occurring together can be used for learning what concepts are similar, what are not similar, not related to each other. Okay? We might not know what they mean, but we can at least say, well, we don't know what X and Y mean, but we know that they're related because they seem to be occurring together. That's essentially this idea of a co-occurrence network. You're essentially looking at correlations. Right? That's another way to put it. So we want to build what is called this co-occurrence network, which is essentially a network of terms, medical terms, or some terms, and how they might be related to each other. So I might, and one way to represent this co-occurrence, this idea of co-occurrence, is what is called is through a graph. Graphs are essentially, graphs contain two things. What are called nodes or dots. These are called nodes. And edges. Edges essentially connect. Now, what the nodes mean and what the edges mean, that is quite, that depends on the context, right? These can mean different things depending on what application you look at. But graphs are abstract data structure that will help you capture some items and their relationships, right? For example, if these are locations of cities, right, the edges could represent if is there a direct highway that connects the two of them. Okay? If these are medical terms, maybe the lines tell you if they're conceptually related, they're medically related, right? So here this would mean this node and this node are related, whereas this node and this node are not directly related. Okay. And you can have numbers associated with nodes. For example, I can have a thick node or a thin node. Thick node might mean they're very strongly related. Thin node might mean, well, they're related but not very strongly. So things like that, right? So it turns out that you can represent this relationship, right, through matrices. That's one of the applications of matrices. So matrices are heavily used in graph theory, okay, to essentially capture relationship between stuff. You can run this. We're going to be using the same data set. So the initial steps are all exactly the same. Then we come to this idea of a co-occurrence network. The idea is again very simple. You have your medical nodes. Each row represents a individual node. we have a bunch of tokens. Again, let's say we have n nodes and we have m tokens. Each token is an individual text. For example, this could be the first token. This token could be, I don't know, headache. So here, earlier what we did was we did count factorization for converting into an n vector. What we will do here, we'll simply ask, we want to know, given a node, we simply want to ask, does a token occur or not? Okay, essentially a binary piece of information. So if I give you the ith node, right? I want to have a vector which only contains zeros and ones. I don't care how many times this term occurs. I only care about whether or not it occurs. Right? So if I have if the ith node returns all zeros, what does that mean? Well, none of the tokens occur in this. If it's all one, all tokens occur. Okay? That's the idea. Okay? So you do this for each token. Okay? Instead of returning a column vector, let's say we return a row vector. We don't return it as a column, but as a row. You can do it the other way around as well. But this is a standard way of doing it, so we'll stick to this. Okay? There is nothing special about representing it as a row or a column. That's all. What is the size of each row that is returned by this process of finding out whether a token occurs, whether the tokens occur or not? It will be m vector, right? Because that's the number of tokens. Okay? Let's say we take each of these rows, right, and we're going to represent that row as y. Okay? This simply means this is the occurrence. I'm going to call this the occurrence row. Okay? This is the occurrence row for the ith row in this matrix, or the ith node in this vector of text. So this will have. Okay? Now, if I stack all of these rows in a block column, right, like this, 1 O n tilde transpose, then I get, what is the size of the matrix I get? No, each of this is a row, right? You have n rows, and each row is a m vector. You essentially have a n cross m matrix of zeros and ones only, right? And what would the ijth element of this matrix tell me? Yes, what does it mean? If it's 0, what does it tell me? If it's 1, what does it tell me? Or in words, can you tell me what the ijth Oij represents? Which word? That's what I'm asking. No, right. That's the element in the Oijth position in the matrix. I agree. But in terms of reports and tokens, right? If you were to write a sentence about what this stands for, what would that be? It's essentially ith token jth report or jth token ith report. So which one it is? Which one is it? So it turns out Oij tells you if the jth token occurs in the ith row or report. Okay? If that's not clear, you should go back and see if that makes sense. And this is important, and you need to understand. You need to be very clear why it is so. Okay, so we essentially now have a matrix. Okay, and if you look at that matrix, by going to a specific element, you'll know exactly whether or not a particular token occurs in a particular report. Okay, right. Now the question is, okay, we have this matrix, but what we are interested in is not whether or not specific tokens occur in specific reports. What we want is, do a pair of tokens co-occur or they don't co-occur? Right? That means what I would ideally like to know is Cij, or I'm going to give a different. I'm going to give different subscripts to this so that it's not confusing with this Oij. CLK. Okay. I want to compute CLK, which is essentially, do the Lth and the kth token co-occur? If it's 0, that means they don't occur together. If it's a large positive number, then it might mean, well, they actually co-occur a lot. And one way, and the way you can obtain this is actually quite simple. And it turns out you can do matrix multiplication is involved here. Right? So this is essentially what we discussed so far. It turns out that you can find out this co-occurrence, and in fact, that co-occurrence that you're looking for, right, will not be a scalar. It's a scalar for a pair of tokens. But remember, you have 50 tokens or m tokens. So ideally, you want whether the first one co-occurs with the first one, which is trivial. It always co-occurs. Whether the first one co-occurs with the second one, with the third one, so on and so forth. And then for the second token, you can ask the same thing. Does it co-occur with the first one, second one, third one, so forth, fourth, and so on and so forth? That means you essentially have a matrix of numbers that tell you co-occurrence of these 50 different tokens that you have, where the ijth element of that matrix that you have will tell you whether tokens I and j co-occur, or how often they occur together. The ith element will of course be always high, right? Because how many ever number times token I appears, it appears that many number of times. It will be equal to the number of times that particular token occurs, right? And it turns out that you can compute this, so you don't have to go back to the report and in each report count the number of times, let's say, token I appears, and see in how many reports token I and j co-occur. You don't have to do that calculation again going through each row. Once you have the occurrence matrix, it turns out you can compute that already. And that you can do simply by this operation. You take the O matrix, you multiply O transpose O. What will be the shape of the resulting matrix? O was n cross m. If you do O transpose O, which I'm calling the co-occurrence matrix, what will be the shape of this? M cross m. And does it make sense that it's m cross m? What is m here? Well, number of tokens, right? So it makes sense, right? And the ijth element will simply tell me, well, whether how many times token I and token j co-occur. Yeah. So here there is a question on, okay, what do elements Cii correspond to? So you can answer all that, right? Another question is C a symmetric matrix? What is a symmetric matrix? Transpose is the same as the original matrix. That's all. Okay. So here you're okay. Here you're asked to verify. You're asked if it's symmetric, and if it's symmetric, the question is, what does it mean, and does it make sense that it's symmetric? Okay. So that you can answer. And you should also try and understand why this operation makes sense. I told you can compute it like this. You should really try and dig and see, okay, why does it make sense that it's defined like this, and what is really going on? And here, because each of those individual elements of this matrix C, right, ij has a specific meaning, and you're interested in the scalar, you should essentially now use the inner product view of matrix multiplication to try and make sense of what that Cij term means, how is it computed from the rows or columns of O, and if it makes sense to you. So it'll turn out, if you remember, theCijth element will be simply the inner product of the ith row of O transpose and the jth column of O. Okay, and those two have a specific meaning, okay? The row and the column. Okay, and you're essentially taking the inner product, and that will give you the number of times the tokens I and j co-occur in your entire data set. Okay, let's say we have two occurrence vectors like this. Okay, case one, we have, let's say, 5 tokens. Case one corresponds to some report, corresponds to some data set where all tokens appear in a particular report. Okay. Now, if you take the inner product between these two, right, both of them will give you 2 as a response, right? But in the first one, this token corresponding to X occurs in all reports. Token corresponding to Y appears only in report 1 and 5. Okay. Whereas in the second case, in the second data set that you have, token X appears in reports 1 and 4. Sorry, 1 and 4. Token Y also appears in reports 1 and 4. So if somebody asked you, do X and Y co-occur in these two cases, you're likely to say, well, in the second case, it looks like they co-occur. Whereas in the first case, you would not say that they co-occur, because there are many cases where X occurs and Y does not occur. Whereas in the second case, whenever X occurs, Y seems to occur as well. Right? But if you simply take the inner product of these two, right, you'll simply count the number of times they co-occur, which is what is given by this matrix, the C matrix. This will simply count the number of times 2 tokens co-occur. But just counting the number of times they co-occur might not be a good idea because of a situation like this. Right? So one way to solve this problem is, well, you don't take just the inner product, you normalize the inner product by the length of each of these vectors. So essentially, you're looking at the cos of the angle between the two vectors. Okay, that normalizes for the length of the vector. Okay? And in this particular case, we know that the cos of an angle between 0 to 360 can be positive and negative, but in this case, it will always be non-negative. Here you're asked to explain why it is likely to be non-negative. Right? So we will actually not work with the matrix O, but we will work with the normalized matrix, because remember, what matters is not how many times they co-occur, how many times a particular vector occurs. It also matters how many reports you have. Right? So we are essentially normalizing each of the columns by the number of reports we have, or number of times number of reports we have. Okay, normalizing it by no, not the number of reports we have. I'm sorry, normalizing it by the number of times that that particular token occurs. Okay. Again, there is another question where again something to do with matrix multiplication. So the final matrix that we will work with is this. Again, a co-occurrence matrix, except that the terms are now normalized. That's all. And if you do this right, you get a huge m cross m matrix depending on the number of tokens you have, and you can visualize this like this. So I've essentially taken all the 50 tokens we have, put them on the circumference of a circle, and whenever a Cij term is large, let's say close to 1, then that would essentially result in a thick black line between them. If it's 0, then there is no line between the two nodes. This is essentially a graph. I'm visualizing a graph. the co-occurrence graph. And anything in between is essentially a different shade of gray. Okay? And when you do this, this is what you find. It looks like there are some dark lines. That means some terms seem to co-occur, some don't. Okay. Again, if you dig a little deeper into this, it might not make any sense. Some of the terms that seem to co-occur. Again, that the quality of this graph depends on the quality of the tokens that you've chosen for your problem. For example, if you look at this, there is a thick line between sprain and tendonitis. Where is that? So tendonitis and sprain, okay, which maybe means something. Maybe they're related because maybe they occur in ortho or something like that. There is another thing between these two terms. You can search for what these are, right? But there are also other examples where the terms itself are kind of very strange. So in the tokens, we have relate and impress. So it's not clear why you would have terms like this in this, but nevertheless, you have those terms. Right? But the idea is, but you get the idea, right? This is essentially how you would build then in a field that you have nothing, you know nothing about. You can at least say something about what things are related and what are not. And one way to do that is what we've shown so far. And in this process, right, and also in the process of clustering, there were some choices that we made as to how we want to capture information in our original dataset. All those little decisions actually matter on the answer that you find for your question, right? So all those steps really matter, right? For example, here we've chosen to use whether or not a token occurs in a report. A better approach would be, well, maybe we should count the number of times like we did before. Instead of finding whether or not a token occurs, we should be counting the number of times a token occurs. And so one way that might be better is if you say two terms co-occur, if we find within a report term 1 occurs 10 times, then I would expect that the second term also occurs 10 times. If it occurs only once, right? And if you only look at presence or absence, then you're saying, well, if the two terms at least appear once in a report, I'm going to say they co-occur. Whereas it's possible term 1 occurred 100 times, term 2 occurred only once. So that is really not a good example of terms co-occurring. So if they're co-occurring, if this occurs k times, I would expect that the other term also occurs more or less k number of times, right? So a better approach could be, well, don't use binary presence or absence, use count vectorization. So instead of the O vector, right? Yeah, instead of counting O, let's just, instead of computing O, let's count the number of times each term appears, right? And then you can do the same process. You should still normalize, but you can then do the same process and then do the whole process again and then see what kind of a graph you get. So that's one approach. Look at it differently as well. Why are we looking at the inner? See, inner product measures is a measure of similarity, right? If two vectors more or less point in the same direction, their inner product is likely to be higher than two vectors that actually are close to perpendicular to each other. So if inner products are a measure of similarity in terms of direction. Another way to look at similarity is just look at the difference between the two vectors. 2 points that are close together in space could be considered to be similar, right? So maybe we should not be doing O transpose O. Maybe we should simply, for each token I, we take the vector corresponding to the number of times it occurs in these reports and compute the distance of that token with let's say another token J. So essentially I'm saying instead of doing OI transpose OJ, compute OI minus OJ and compute the norm. And that norm is again, you're free to choose. You do the first norm, second norm, infinity norm, any of those. So the point I'm trying to make is in all these analyses, right, there are lots of choices that we need to make, and those choices can lead to different results, right? And in fact, in the assignment, or maybe in the previous one as well, you're asked to explore. For example, at least in the second one, you're asked to explore instead of using the normalized inner product to quantify occurrence, you can instead use the norm. Essentially, take the difference between two OIs, OI and OJ, and then compute the distance using some norm, and you can use the first norm, second norm, or the infinity norm, and then see how see if the choice of those leads to different results in your final graph. So those are things you are asked to implement as part of this assignment. Okay. All right. Okay, that is essentially everything that we wanted to cover for the first 3 modules. Now, everything you need to do your assignments is also now covered. So you should really focus on getting your assignments done and submitting them on time. Okay? And tomorrow we'll start with orthogonality. Yeah. Thank you. Yeah, please try and open this. If you're not able to run it, come and let us know. Fix it.